Embedded C is a specialized version of the C programming language, designed specifically for programming microcontrollers and embedded systems. Unlike standard desktop C, Embedded C allows direct access to hardware through memory map registers, making it ideal for controlling devices with limited resources such as RAM, flash, and CPU. In these environments, real-time and deterministic behavior is crucial, and often there is no operating system or only a minimal real-time OS. For example, toggling an LED on a microcontroller involves writing directly to a hardware register using the volatile keyword to ensure the compiler does not optimize away critical operations. This direct hardware interaction is what sets Embedded C apart from its desktop counterpart, making it essential for anyone working with embedded devices. Understanding the target hardware and memory model is fundamental. In Embedded C microcontrollers typically have separate regions for flash, where code resides, RAM for data, stack and heap, and memory map peripheral registers. For example, defining a UART peripheral involves mapping its base address and using typedefs to describe its register layout. Data types are equally important. Using fixed-width types like UNT8T or UNT32T from STDIN, H ensures portability and predictable memory usage, which is critical for protocol handling and memory-constrained systems. Avoiding generic int or long types helps prevent subtle bugs due to varying sizes across platforms. These practices lay the groundwork for robust and portable embedded application. Embedded programming, qualifiers like volatile and const play a vital role. The volatile keyword tells the compiler that a variable can change at any time, such as when updated by an interrupt or hardware. This prevents the compiler from optimizing away repeated reads or writes, which could lead to missed hardware events. Combining volatile with const is common for read-only hardware registers. Structs are often used to map peripheral registers, providing type-safe and readable access. For example, a UART peripheral can be represented as a struct with volatile members for its data and status registers, making code both safer and clearer. These techniques are foundational for reliable embedded software. Manipulation is a daily task in Embedded C, used for setting, clearing, toggling, or testing individual bits in hardware registers. Macros like set, CLR, and tog make these operations concise and less error-prone. Understanding structure, padding, and alignment is also crucial. Compilers may insert padding bytes to align data members for faster access, which can increase memory usage. Ordering struct members from largest to smallest can help minimize wasted space. In some cases, such as protocol packing, Hashpragma-Pack is used to remove padding, but this should be done with care to avoid performance penalties. Mastery of these low-level details is essential for efficient embedded programming. Interrupts and timers are at the heart of responsive embedded systems. Interrupt service routines (ISRs) must be short and efficient, often using volatile flags to signal the main program. Hardware timers provide precise delays and periodic actions, while peripherals like ADCs and UARTs are accessed through memory map registers. For example, ADC readings and UART communication can be handled using either blocking or interrupt-driven approaches, with circular buffers for efficient data handling. Direct memory access (DMA) further offloads repetitive data transfers from the CPU, improving performance for tasks like streaming sensor data. These mechanisms enable embedded systems to interact with the real world in real time. Startup process in embedded systems involves initializing the stack, setting up memory sections, and jumping to the main function. The linker script defines how code and data are placed in memory, which is vital for custom hardware. Debugging embedded systems requires special techniques. Use volatile for shared flags, prefer hardware timers, and DMA for reliability, and keep ISRs minimal. Unit testing, error logging, and separating hardware abstraction from business logic all contribute to maintainable code. By following these best practices, developers can create robust, predictable, and efficient embedded applications that are easier to debug and extend. Sum up, Embedded C is all about writing safe, predictable code that interacts directly with hardware. Key concepts include using fixed-width types, understanding volatile and const qualifiers, mapping registers with structs, handling interrupts and DMA, and mastering the startup process. By focusing on these areas, beginners can build a strong foundation for embedded development. For further practice, try exercises like blinking an LED with SysTick, implementing UART echo with interrupts, or setting up DMA transfers. Exploring these hands-on examples will deepen your understanding and prepare you for more advanced embedded projects.